So hello everyone, this is lecture 47 for the mathematical physics. In the last lecture we were discussing some questions based on the residue theorem. So in today we will learn some very important application of residue theorem. Means we will apply this residue theorem or the complex integral theorem in the real integrals or the definite integrals. Means you have seen some kind of integrals like in the trigonometric functions, in the exponential functions. So how can we solve those integrals using the help of complex integrals or the residue theorem? So first we will see some special cases like trigonometric integrals. So if you have this kind of function is in the form of sine theta or cos theta, and limit is 0 to 2 pi, only this limit should be there, then you can solve this by this method. Then range is 0 to 2 pi and this kind of integral you have. Then how you can solve using this residue theorem? So see, this f function will be single valued function. If it is 0 to 2 pi, then sine function and cos function will be single value function, and d theta. Now it is 0 to 2 pi, so you can consider a unit circle because that will also give you theta 0 to 2 pi. So consider a unit circle oriented counterclockwise. So we considered this circle, and now this circle is in the complex plane, we considered it, and z equal to nothing but exponential I theta. So mod z will be 1 because that's why it's a unit circle. So these are the conditions you will guess. Now you can solve this. Let's see how we can solve this by using these conditions. Now from here dz will be I exponential I theta d theta, just simple differentiation, and from here d theta will be minus iota dz by z. This exponential I theta is nothing but z, so it will give you d theta equal to this. Now you remember these sine and cos in the exponential form. Sine theta will be exponential I theta minus exponential minus I theta divided by 2 iota, and same for cos theta, just here it will be plus and no iota here. So you should remember these formulas every time. Now in place of exponential I theta we will write z, so it will be z minus 1 2 iota and z plus z minus 1 divided by 2. So you can write sine theta in form of z and cos theta in form of z. Now you will just substitute in this function wherever you are getting sine theta and cos theta, you will substitute these values, and then in place of d theta it will be minus iota dz by z. So you will get a complex function. So now that complex function can be solved using the residue theorem. So you will get something like this for the cos theta and the sine theta. It is for sine theta and cos theta, and dz by z minus iota. So it will be like in the form of fz divided by z. Now you are very much familiar with this kind of integral. We have solved many questions based on this. Now we will use the simple residue theorem. It will be minus iota 2 pi iota and residue of this fz by z. So it will give you the integral within unit circle. Means when you find the residue, so only find at those points which are lying inside the circle mod z equal to 1. Okay, because we are solving this for this kind of circle. So let's see one example. Integral we need to find is 1 upon 5 plus 4 cos theta. Now this is a definite integral. How you can solve this? Using complex integrals. So just put z equal to exponential I theta. So d theta will be minus iota dz by z. So in place of d theta it will be minus iota by z dz, and in place of cos theta it will be z plus z minus 1 divided by 2. Now see, we will just simplify this. 1 upon z will give you z square plus 1 divided by 2z, and 2z will give you the 2, and here it will be z only, so z will go this side 5z, so this will reduce to this equation. Okay, and minus iota on the numerator. Now write in the quadratic equation 2z square plus 5z plus 2, then take 2 common and you will get this kind of form. So you will always need to find means make this coefficient 1 here. With the z square, the coefficient should always be 1. Now see, this is a form of complex integral. So first you need to find the singular points. So singular points will be z equal to minus 1 by 2 minus 2. Simply solve for the quadratic equation, you will find these 2 points. Now you need to see that which point is lying inside the circle. So minus 1 by 2 will lie in the circle of unit radius. So you need to find the residue only is this point. So what will the residue? So first this can be written in this form, z plus 1 by 2 z plus 2. So because these are your roots. So using the limit you can find the residue. You just need to find the residue now. You have solved many questions based on this. So how you can find the residue? At z equal to minus 1 by 2 it will be limit z tends to minus 1 by 2 z minus 1 upon 2, it will give you z plus 1 upon 2, and this will be written in this form. This will cancel out and substitute in place of z minus 1 by 2, so you will get 2 upon 3 as your residue. So this integral will be 2 pi iota multiply 2 upon 3. So answer will be 2 pi by 3. So this is your integral. That's how you can solve the definite integral using the help of complex integrals. Let's take one more example. Cos 2 theta d theta phi minus 4 cos theta. So put z equal to exponential I theta. So z square means here we have cos 2 theta. So z square will be exponential 2i theta. And this is nothing but means z square is equal to exponential I2 theta. So cos 2 theta can be written in this form, exponential I2 theta plus exponential minus I2 theta divided by 2. Now in place of exponential I2 theta we will write z square here, z square plus z minus 2 divided by 2. So we'll just substitute in this value. So it is integral z square plus z minus 2 divided by 2 minus iota. In place of d theta it will be again minus iota dz by z, 5 minus 4 z plus minus 1 divided by 2. So we'll just simplify this equation. We will again do this here. 1 upon z will give you z square plus 1 divided by 2 will give you here 2, and it will be like this. Same for this, 1 upon z square will give you z4 plus 1 divided by z square, and minus iota by 2, and this z will be here. So this 2 is here. So I just simplified this equation and it will give you this equation. Then after this z will go this side, minus 2z square plus 2 plus minus 1 will give you minus 2. So you will get this equation. Now you will take 2 common, means make this coefficient 1. So you will take minus 2 common. So it will give you z square minus 5 by 2 z plus 1. Now what you need to do, you need to find the residue for this. So first you need to find the singular points. So singular points will be, means this can be written in this form, z square z minus 1 by 2 z minus 2. So singular points will be z equal to 0, z equal to 1 by 2 and z equal to 2. So in these points only these 2 points lie inside the circle. So you need to find the residue on only on these 2 points, and just substitute in the value 2 pi iota multiply residue and multiply iota by 4 will give you answer. So how you can find the residue now? For this z minus 1 upon 2, you just need limit z tends to 1 upon 2, z minus 1 upon 2, it will cancel out. And place of z 1 upon 2 here you will put, and 1 upon 2 here, 1 upon, okay, and 1 upon 2 here. So that will give you residue at 1 upon 2. Now to find the residue at 0, it is z square. So now it is a something pole of order 2. So how you can find this? You will use the formula we already discussed, 1 upon n minus z naught factorial. Okay, n minus 1 factorial, and d n by means n minus 1. You remember this formula from here. Let me give you this formula. So here it was. For n, means for simple you can use this formula, z minus z naught fz. If it is some n power, then you will use n minus 1 factorial and the derivative with respect to n minus 1, order of n minus 1, and z minus z naught and fz. So for z square you will use this formula for this, and for this simply you will get your answer. So for z equal to 0, it will be 1 upon n minus 1 factorial. So order is 2, so 2 minus 1, limit z tends to 0, d by dz, 2 minus 1 will give you first order derivative. So z minus 0, z4 plus 1, and we put the values here. So after solving this you will get 5 by 2 as your residue, and for this one z equal to 1 upon 2, after solving this you will get minus 17 by 6 as your residue. So it's just simple, 2 pi iota and iota by 4 from here, and the sum of residue. This will be your integral. So it will came out to be pi by 6. And so let's see some tricks also. These are very helpful to solve the question fastly. If integral is given in this form, 0 to 2 pi 1 upon a plus b cos theta, you can solve this by this method we already discussed. But there is trick, if a is greater than b here, and if you are getting here cos theta or sin theta, then same you can use the direct formula, that is 2 pi divided by under root a square minus b square when a is greater than b only. So this is applicable when a greater than b only. So use this direct result to solve the question fastly. So just take an example, it is under root 2 minus 1 cos theta. So it is under root 2 is greater than 1. So you can write directly 2 pi over under root square of this 2 and minus square of this 1. So it will give you 2 pi. So this will be your integral. You can find this. You will get the same result by this method also. So that's the trick. Now, so here we end with the trigonometric functions. Now let's see some more kind of integrals. Now if you need to solve this kind of integral, where limit is minus infinity to infinity, and this is definite integral fx dx. So now you need to solve this kind of integral. So how you can solve this? Means now it is on the x-axis. from minus infinity to infinity, and there is some function fx. So how you can solve this? So see, to solve this in the complex integral, you need to make a contour first. So to make a complete contour, you can make it either on the above of the x-axis or below of the x-axis. And using the solve means then you can solve this complex integral and you will get the same result. So either with the upper half of the circle or the lower half of the circle, you will get the same result. So let's see how we can make the contour. So these conditions should be satisfied, only then you can use this thing. So fz is analytic in upper half plane. So when you make this upper half plane, then fz should be analytic in a upper half plane only at some points for a finite number of poles. Means at some points you will have singularity and no pole on the real axis. On the real axis there will be no pole because it is x-axis and there is this upper half plane. So it can be non-analytic at some points, but it will be analytic at all other points. And this condition also should be satisfied when z tends to infinity, then z fz should be equal to 0 in the upper half plane. In the upper half plane you can see that what is the range of theta? Theta is 0 to pi. So theta is nothing but argument, so theta will be greater than or equal to 0 and less than or equal to pi, and this should be 0 in the upper half plane. When these conditions are satisfied, then how you can write this integral? Means now the complete integral will be contour C fz dz will be of this contour. Now this can be written in this form: limit r tends to infinity minus r to r, then this contour, open contour. So limit r tends to infinity minus r to r fx dx plus limit r tends to infinity this cr fz dz. So if now you can write this contour in this form. This is a simple case, means it is a this this is already applicable in every condition. Means you can write any closed contour in two forms with this real axis and this sum. Okay, now see this second part, limit r tends to infinity fz dz. So when these conditions are satisfied, then this second part will be 0 always. Only when these conditions are satisfied, this part will be 0. So whatever you are getting from here integral will be equal to this integral, and we need to find this integral only because it is nothing but minus infinity to infinity fx dx. So we need to find this integral, so we'll solve only for this and we'll get the same result, and this will be 0 because these conditions are satisfied. So let's see what I'm talking about. Means when this will be 0, then this will be equal to this, and this integral can be solved by 2 pi iota multiply residue at all the points, at all the poles. So this fz dz cross control will be equal to this one, and this will be equal to 2 pi iota residue of fz at point in the upper half plane. So see, we can find this integral just solving for this integral. So this was a very helpful result. Let's see one example. Means first let me prove you that how, if this condition is satisfied, z fz equal to 0, then this will be 0. So why it is becoming 0? So let's say z equal to r exponential I theta and theta is 0 to pi, so we have this semicircle because theta is in this range. So now let's take this integral, this one. So limit r tends to infinity cr fz dz. Now the mode of this will be less than or equal to when you take this limit inside, so it will be of this form, and this is mode. Now see, this iota exponential I theta will give you mode equal to 1, and d theta integral will give you what? It is 0 to pi, so it will give you pi here. So this pi will came out and this will be 1, so it will be only remaining r exponential I theta. So if you just multiply with exponential I theta and don't make it 1, then r exponential I theta and f r exponential I theta, it is nothing but z fz form. So this will be 0, means this will be 0 only when this condition is satisfied. So if this is equal to 0, then this will be equal to 0 because this is less than or equal to 0 and this is mode. So only for 0 this condition will be satisfied. So see, if this condition is satisfied, then this will be 0. So that's what we proved just. Okay, so always when we are getting some fz or the fx, so we'll check that if z fz is equal to 0 or not for this limit. If this is equal to 0, then we can apply this condition and we can use this formula only when this is equal to this. So like you can take fz equal to 1 upon 1 plus z square, then multiply with z, z will go to denominator 1 upon z plus z. So at z equal to infinity, 1 upon z will be 0 and 1 upon z will be 0. So this condition will be satisfied, so you can use the formula for 1 upon 1 plus x square or z square. So see, we will see some examples and you will understand. Now we have this, means integral is in this form, 0 to infinity 1 upon 1 plus x square dx. Now we need to solve this integral. So see, we study this formula for the minus infinity to infinity, so we need to change this in that form. So if you know the properties of integral, then this is a even function, f minus x will be equal to fx, so you can write this function as this form, minus infinity to infinity, and this, because this integral is equal to 2 0 to infinity, and then this will cancel out and it will give you again this form. So that's how you can write in this form. Now you have this integral in the form which you already know, so you will make this contour. Now this will be in, let fz equal to this, means fz equal to 1 upon 2 1 plus z square, means in place of x we will write z, simply z. Now we will find the singular points, means in this plane. Now in this contour, this is the x-axis, it is no pole on this x-axis, and 1 plus z square will give you z equal to plus minus iota. So we need to assume this, because see here, whatever fx you are having here, you are having fz here. So we need to make, in place of x, just write z. So it is 1 upon 2 1 upon 1 plus x square, so it is 1 upon 2 1 plus z square. Now find a singular point, z will be plus minus iota, and you have this half semicircle, so plus iota will lying inside and minus iota will not lying inside, so you need to find residue only on this point. And see, this condition is satisfied here, z fz equal to 0. How? If you multiply with z here and fz is this, so z will go into denominator 1 upon z, and here it will be z. So 1 upon z will give you 0 at z equal to infinity, then this will only z remaining, so 1 upon z at z equal to infinity, this will again give you 0. So this condition is satisfied, means we can write this into this form. Okay, so that was the condition, because that was the thing, means this will be 0 in this place. We already proved this, if this is equal to 0 z fz, then this will be 0. So now just solving for x equal to z here and minus infinity to infinity, this will give you the value for this. So we need to find the residue at z equal to iota. So let's see. So 1 upon 2 1 plus z square will be equal to this, means this is the general formula at the x-axis plus that contour, and this contour will be 0. So we need to find, means this integral will be equal to this integral, and this integral can be solved using just residue theorem. So at z equal to iota, it can written as z plus iota z minus iota, so we'll use the limit term, so z minus iota will cancel out and z equal to iota will give you 1 upon 4 iota. So we have solved many questions based on this, you know how to do this. Now this is your residue, so integral is nothing but 2 pi iota multiply residue is 1 upon 4 iota, so this will give you pi by 2. Now this integral is pi by 2, this one, so and this is 0, so this integral is also pi by 2, and this is what we need to find, because now this 0 to infinity will give you 2 here and 2 will cancel out, it will be 0 to infinity 1 upon 1 plus x square will be equal to this. So this will be your value for this kind of integral. So that's how you can solve the definite integral of this kind. Now you can also take this lower half, means either you can solve in this way, or you can solve in this way. So let's take this closed contour now, minus r to r, then r to this contour. So now it is in the clockwise, so we'll get the minus 2 pi iota and the residue, and residue will be now at z equal to minus iota, because now this plus iota won't be lying inside, the minus iota will be lying inside. So at minus iota you will get the residue as your minus 1 upon 4 iota, and just multiply I will be 2 pi iota multiply 1 upon 4 iota, and minus will cancel out, you will get the same integral pi by 2. Okay, so that's why we can apply any contour here, either on the upper half plane or the lower half plane. Okay, now you must remember this formula. This is a fastest solution formula. If you have this kind of integral, x to the power 2m, x to the power 2n plus 1, and where this m is less than n, then the integral will be 0 to infinity dx pi upon 2n sine 2m plus 1 divided by 2n pi. So you can use this formula, like here we have this 1 upon m plus x square, so here x equal to 0, so upper power is 0, lower power is 2 into, so here it is m equal to 0 and n equal to 1, so m equal to 0 and n equal to 1 will give you here sine pi by 2, and n equal to 1 here, so it is 1 and pi by 2, so you will get the same value as you are having here. So just remember this formula, this is derived from this actually. So that's it for today. In the next lecture we will see some more kind of this kind of integral, like in exponential, fx exponential something, and that's how we'll move, and the last we will see the branch point singularity. So that's it for today. Thank you everyone.